The discoveries of the James Webb Space Telescope have sabotaged the case for the theory of prehistoric cosmic detonation. The James Webb Space Telescope has recently conveyed an exhilarating disclosure that is sending shock waves through the universe of material science. Through a single amazing picture, it has obliterated long-standing discussions, leaving researchers paralyzed. The period of theory is over, as Webb's most recent catch is both outwardly enamoring and a game-changer that vows to upset our impression of the real world. What searing discussion among researchers has this picture definitively finished? And in what ways is the shocking picture caught by the James Webb Space Telescope rethinking how we might interpret the universe? Join us as we dig into why James Webb's discoveries are stopping discussions in material science. With a breaking picture, the major issue with astronomy is that researchers can't come to an understanding about how old the universe is or, on the other hand, the way in which quick it is growing. This unanswered peculiarity has confused researchers across ages, driving them to lead different exploration to find answers. Cosmology is the field of research that spotlights on getting it, how the universe was made, the way things are set up, and how it has changed over time. Ultimately, it explores the way that it will end. This field has seen critical advancement in the past 100 years. The presently acknowledged cosmology model, the theory of how things came to be, proposes that the universe has been growing from a very hot and thick introductory state for about 13.8 billion years. This development is estimated by the Hubble constant, which shows the speed at which the universe is extending. Anyway, estimations of the Hubble constant are not direct. Estimating the Hubble constant can be extensively categorized into two gatherings: local estimations and early universe estimations. Local estimations include the investigation of cosmic bodies. For instance, Psi-8 variable stars and type Ia cosmic explosions act as standard candles to gauge the Hubble constant. Because of their splendor, stargazers can measure how the universe's extension influences the rates of these objects to derive their distances and hence compute the Hubble constant. The second gathering is the estimation of the early universe. Researchers use perceptions of the cosmic microwave background radiation, CMB, the luminosity of the Big Bang, found during the 1960s. The CMB shows the microwave radiation of the early universe when it was simply 380,000 years of age. By estimating the small temperature and polarization variations emanated by the CMB, cosmologists can lay out the age of the universe and its pace of development. However, here's the issue. The consequences of these two techniques do not connect. The outcomes noticed through local estimations affirm the universe is growing quicker than what we gauge in view of CMB information. Due to these distinctions, researchers have been striving to reveal the reasons behind the outcomes. As such, further research is being led to learn more about the secrets of the universe. As things stand, the distinction in estimations shows that there is either new science we have close to zero insight into or botches in one or both ways by which we are estimating things. On account of the James Webb Space Telescope, we can see into the dark universe more clearly than any time in recent memory. Before, the telescope can show the slightest and most far-off components, planets, and cosmic systems we wouldn't have thought it was feasible to see due to its capacities. Researchers normally expected that information from the JWST would help us in definitively computing the Hubble constant. Anyway, the main wave of information has astoundingly made matters more muddled. They have given us new experiences that are not rational with what we assumed we knew. Might this information at any point lead to another hypothesis and reform how we contemplate space? Assuming this is the case, we could have to audit how we might interpret how the universe works. For example, we may find particles and powers that have never been noticed, or it could mean that dark energy, an unexplored world factor responsible for the speeding up extension of our universe, should be reconsidered. Up until this point, the manners in which we think about space have advanced as we proceed to find new things. For instance, in 1965, when specialists found the cosmic microwave background radiation, it filled in as a strong basis for the thought of the theory of the universe's origin. Before then, researchers felt that the universe was timeless and subsequently was continually growing at a uniform rate. However, the new proof demonstrated that was not true. Likewise, when we found out towards the end of the 1990s that the universe was constantly growing at a speeding up rate, it further changed our understanding. we found dark energy and its effect on the universe's development. Accordingly, every time we learn something new, we question whether it squeezes into our ongoing structure. If not, we think of new ways to deal with comprehend the universe better. To this end, the issue we are facing in cosmology today could prompt the disclosure of the most superb answers for the universe. While the issue is testing, it is additionally thrilling, as it constrains us to foster all the more mechanically progressed apparatuses to investigate space. This cosmological difficulty likewise joins the logical community from various nations, as each researcher wants to find out about the universe. In particular, it shows that science is continually changing and developing as we more deeply study space. Alongside the Hubble tension, there is likewise a worry referred to as the S8 tension. This is concerning the spatial circulation of issue in the universe. This can be utilized to draw a primary image of the universe and perceive how it has advanced. Space experts allude to this peculiarity as knottiness because there are areas of room that have parcels of systems firmly gathered while other regions are meager. Researchers will utilize various strategies to quantify this knottiness, and one way is to check how the light from far-off universes gets bowed by the different gravity of enormous items, for example, cosmic system groups. This twisting, known as gravitational lensing, gives us a method for examining where dark matter is given that it is imperceptible as it doesn't produce light. Scientists additionally utilize the Astronomical Microwave Foundation, CMB, a glimmer from the outset of the Big Bang. This light has been moving for roughly 13.8 billion years, bearing news from the early universe. Through CMB examination, physicists can unravel how the universe was knotty in its introduction to the world, which ought to match the observational unevenness of the universe at the present time for an enormous scope. However, here's the catch. These outcomes additionally don't adjust. The CMB's knottiness, presented by the non-round gravity appropriation model, suggests that the matter dispersion at the beginning phase of the universe was more homogeneous contrasted with the one noticed involving gravitational lensing. As such, we can figure that there is something different that we are not considering in the clarification. This takes us back to the idea of dark matter. What precisely is dark matter, and how can it work? The truth is the issue remains unanswered. Anyway, all hope isn't lost, as the James Webb Space Telescope, JWST, is set to rethink the field of stargazing with its exceptional high goal and awareness. The telescope will look at early times of the universe and examine the principal worlds and stars framed. This makes it conceivable to further improve estimations of enormous extension and matter appropriation. These basic questions will require exact observation and, possibly, new approaches from a hypothetical point of view to figure them out. Whether or not the end is seeing more significance to dark energy, finding totally new physical science, or in any event, acquiring a superior comprehension of dark issues, the implications will be expansive. Processing the secrets of the universe is like figuring out a zillion-piece puzzle blindfolded. Researchers should be visible as careful investigators who are centered around and fixated on addressing these secrets. The most recent endeavor called Project Flamingo is evidence of NASA's strengthening energy for logical investigation. Utilizing one of the world's most profoundly acclaimed supercomputers, arranged at Durham College in England, Project Flamingo is a totally awesome accomplishment in the realm of computational advancement. It costs more than 50 million hours of PC time and highlights 30,000 processors and counting. The activity features the academic local area's resolution to investigate the universe completely, significantly zeroing in on dark matter. Dark matter, the puzzling substance that neither produces, ingests, nor mirrors light, is surmised to exist because of its gravitational effect on noticeable matter. Its slippery nature continues to interest researchers. Anyway, the methodology of Project Flamingo is unique in relation to past recreations. It includes all potential types of inestimable components, from worlds with the most unique gas content to stars and dark openings at the focus of the universe. Through such a coordinated strategy, the ongoing change in the portrayal of the universe was made from an essential milestone sketch. The inspiration driving aggressive undertakings like Project Flamingo is clear, to explain infinite contentions where the estimations appear to be flawed and do not fit into the construction of the universe. This divergence in estimation proposes a key misconception in our ongoing appreciation of the universe's functions. In the event that these measurements can be contrasted with melodic types, they are like jazz and classical, each having its own procedure albeit still related. Flamingo endeavors to join these different perspectives and hone our individual impression of the universe. Anyway, in spite of its refinement, the enormous strain perseveres. This pressure keeps on existing as lowering proof that we presently can't seem to tackle a significant part of the mystery that encompasses us. The universe appears to be reluctant to exchange its privileged insights with us. Very much like that, as we add each new piece of information and recreation model to our toolkit like Flamingo, we might see the odds that the universe holds close to the vest change. At last, with the discoveries of the James Webb Space Telescope and the continuous revelations that are yet to come, we might see the ongoing story of cosmology morph into another format. Despite the extraordinary advances in science, researchers are never truly fulfilled. As with every revelation comes a horde of new inquiries that need answers. This delightful riddle prompts us to see how dynamically we can dissect the universe in which we live, from the birthplaces of galaxies to the perspectives of dark energy, each remaining solitary yet closely intertwined in a symphony of cosmic discoveries.